Good morning, good afternoon, good evening, good wherever you are, and welcome to another SNIA webcast. This one is from the Cloud Storage Technologies Initiative, the CSPI, and it's on the impact of artificial intelligence on storage and IT. That's just making sure you have the right presentation. It is, by the way, April the 1st. I think we've all done the jokes this morning, certainly the morning where I am. So this presentation will be pretty joke-free. However, we hope it's suitably entertaining. So, without further ado, let me introduce, first of all, myself. I'm McDonald. I'm the chair of the SNIA CSPI, and I work for NetApp. I'd also like to introduce Glyn Bowden, who is the Chief Architect, AI and Data Science Practice from HPE. Good afternoon, Glyn.
Hi, Alex. Hi, everyone. Hope we're all keeping well.
And James Myers, who's Director, Data Center Storage Solutions Architecture at Intel. It's good morning for you, isn't it, James?
It is good morning, and it's a bow tie morning.
Bow tie morning. Excellent. James is not visible to you apart through the medium of his photograph, but I'm assured he is wearing a bow tie. He tweeted it out this morning. So, just to give you a brief overview of the SNIA legal notice. This presentation is basically copyrighted SNIA, and you can use the accompanying download. You'll find a download link, and you can use that as long as you give this attribution. There are no warranties expressed or implied. If anything you employ this against breaks into two parts, both parts are yours. They're nothing to do with us. Just a little explanation as well about the interface. There are a couple of things you can do for us. First of all, if you want to ask questions, there's a question button. You can ask questions at any time during the presentation. And if they appear in the right sequence, we'll answer them at the time. If we have any time, which I doubt towards the end, we can answer them there. But we will be collecting up all the questions and presenting a blog after this presentation. And I'll explain where that is when we get to the last few slides. And secondly, you can rate this on the way out. Rate the presentation from 1, which is, I could be doing something much more profitable, to 5. This is excellent, more please. Now, the other thing that you might want to do as well, if you think the pictures or the screen area is a little too small for your taste, then simply you can enlarge it to an entire full screen, and you should be able to see a bit better picture of the slides that we're presenting if you think the detail is a little too small. SNIA, what is it? Well, it's the Storage Networking Industry Association. It's about 185 industry-leading organizations that have come together to promote and collaborate on presenting the industry with industry-neutral information about storage. We've got about 2,000 active contributing members from across those companies and over 50,000 IT end users that we communicate through the media and newsletters and the website on a regular basis. The CSPI itself is to do with cloud storage technologies. Our role in life is to educate on cloud storage, and to support and promote business models that make up cloud infrastructure, things like Kubernetes and object storage, to try and understand hyperscaler requirements and your requirements, as smaller business usages of cloud, and to incorporate them into standards and programs, and to collaborate with other industry associations where appropriate in delivering this message. So, without further ado, I'm going to hand over to Glyn. Glyn's going to start us down this process of what is intelligence, artificial intelligence, machine learning, etc., etc. He's going to take us through the introduction to this presentation. Glyn, over to you.
Thanks, Alex. So what we'd like to do today is talk really around the impact of artificial intelligence, and in particular machine learning, because artificial intelligence is a very wide domain of technologies and methodologies. But with a focus on particularly machine learning, which seems to dominate the practice today. So what we're going to look at is what it is, where it's come from, why we need to care about it today, but more importantly, what makes up a full solution. So there's areas people particularly focus on. We're going to look at what the wider picture is, and then from that infer how does that impact the infrastructure that we're looking after, how does it impact the storage platforms that we need to manage, and what can we think about as we move forward in this world and figure out how to build new data platforms to deal with this new technology, new methodology of gaining value from our data. So I think we can start off with the very first question, which is what is intelligence? They seem to be devoid in a lot of conversation I'm having currently, but really it's the ability to learn. It's the ability to infer an action based on the data you're given. So to apply context to that data, if you will, to be able to figure out what to do next. So without being explicitly told, you can figure out from previous experience and also from logical pointers in the environment and in the kind of experience you're having at the moment, how you need to act next. And that's traditionally how human beings manage it, it's how animals manage it, but it's not necessarily how traditionally computers have managed things. With computers, the way they've moved forward is all around being programmed. So they're given a very specific set of instructions, a very specific framework in which to move forward and create the logic that they're executing against. And that can be challenging when it comes to problems that we don't know how to solve as human beings, or the amount of data within that problem set is too large that we can't encompass that as a human brain. So we don't necessarily know how to engage with the problem. We certainly don't know how to build the program to solve that problem. So what intelligence, when we look at artificial intelligence from a computing perspective, is really around how do we enable a computer to do that learning? How do we give it the ability to look at data and infer from that data the types of algorithms and the types of mathematics that need to happen in order to come to the best result? So what we give it is a set of data, and we give it desired outcomes. In some circumstances, we can give it training data, so we can teach it from experience that we already have. In other circumstances, you rely on gaming the computer almost and have it be rewarded for getting the right outcomes, but you don't necessarily teach it how to get there. So that's the difference between two different types of machine learning. And we'll talk a little bit about that as well. The ones you tend to hear a lot around are visual perception or video analytics, speech recognition and natural language processing, and the ability to make decisions. When you look at machine learning, particularly as a domain within artificial intelligence, what you end up with isn't necessarily a black or white answer. It's usually a set of probabilities. So the probability that something is true and the statement is generated. So if you're talking about cat pictures, and when we're talking about AI, it's mandatory that we talk about cat pictures. If you're looking at a picture or a photo and you're deciding whether or not it's a cat, the answer will be a yes or a no, as well as a probability of how accurate that model thinks that it is on that answer. And by using that, you can then start tuning those models to become more and more accurate. So that's kind of artificial intelligence and machine learning at an extremely high level. AI isn't new, though. It's been around for at least 50 years. I think we're moving towards 70 years, actually, because it was around in the 50s originally. And so the term was introduced in 56 by a guy called John McCarthy, who was an American computer scientist. And it was when he started to think about how he could get computers to behave in an intelligent way. The original goal, and the goal still today for a lot of people when they look at artificial intelligence, is to get the computer to act like a human. So to get the brain of a human digitized in some way. Now that's not where we are in AI and ML today. We're far from that. We don't have cognition within a computer. What we have is the ability to process state and to figure out patterns in order to get us to the desired state. So and it's very domain specific usually when you're training models. So they can do one thing very well, but they don't have the ability to learn new activities and new techniques based on inference from one technique. So we're not there at full intelligence. We're focused on very domain specific pieces. You can see that artificial intelligence has been a domain for a long time. There's been a lot of work that's gone into it, and it's had kind of peaks and troughs. They call it the AI spring and the AI winter as we get all excited about new technology coming out and new abilities, and then we get all disappointed when it's not quite the full intelligence we thought it was going to be. We're in the machine learning and deep learning phases at the moment. So deep learning is actually, I refer to it more as a marketing term. It's still machine learning, but it's using machine learning with multiple layers. But deep learning isn't necessarily a thing in and of itself. It's no different from machine learning in a sense. It's a set of techniques that might just go a little bit deeper in terms of the number of layers you have in networks and things like that. But we're really at that phase at the moment where we're bringing large data sets to this kind of machine learning technology set.
And so with that, I'll jump in and start to share a little bit. So you heard a little bit about the history of artificial intelligence and machine learning, but what's really happening in the market right now? Is this really something that matters? And obviously from the numbers, it is. Everyone's talking about it, and obviously quite a few here today to listen to this, but what's the why behind that? Well, it's the top right corner, 84%. So Accenture has been surveying companies, and they all think, 84%, that's nearly all, think that artificial intelligence has to be enabled and utilized in their business in order to help their business grow. So that's a critical capability as far as 84% of the companies. And then where are people at with their deployments? Well, it's about half and half. Both McKinsey and KPMG have done surveys, and the surveys pretty much gave the same answer. Half of the companies already have some sort of AI, and they're growing more and more because they like it. The other half are going to. There's not a lot of people talking about decommissioning or repatriating as it is in the cloud market. Everyone is going in, and maybe we haven't hit the trough of disillusionment yet, but I think some of these companies have, and they're still continuing to deploy. So it's a good sign with a tremendous amount of interest. And a lot of that interest also comes from the financial aspects of the expectations of this technology. All sorts of companies out there are seeing new and new usages, all sorts of different types of usages categorized, and there's lots of taxonomy around it. But this is a report by Tractica, who is an analyst firm that's been very focused on the AI market. And the important thing to think about is just how tremendous the growth is. It's very easy to publish a large growth number if you're starting from a small number. But if you look at that axis on the left, these are not small numbers. Even in 2020, we're starting from a position about $15 billion, billion with a B, in terms of investment going into this technology. And that's growing at nearly a 40% rate. That means over the next 5 years, it's going to have huge impact. You can see out in 2025, the markets for this is probably $120 billion. And that's what people are predicting. And so that's why everyone's so excited about this. They see it as a core part of their business, and they're investing, and everyone sees the investment is going to just continue for the next several years at a rapid clip. Now, what's important with that then is starting to define some taxonomy. So we're going to get into the technical start of the presentation here. We have to be talking a common language so that we can understand that. And there are a few terms that have been broken down in this market in terms of what does AI, machine learning, and deep learning really mean. And you know, as Glyn highlighted, deep learning really is a marketing term, but we are trying to put a category around the sorts of things that we put into that, lump into that. So if you think about AI at the biggest picture, there's 4 different general categories. There's supervised, unsupervised, semi-supervised, which is a mix of the two, and then reinforcement learning sorts of ways of doing artificial intelligence or learning from data. And the differences are relatively straightforward. The first, supervised learning, it means you have fairly well-structured data that's labeled. And so this is traditionally used in traditional analytics or advanced analytics and dashboarding that you're running the business. Sometimes you're using some trending analysis and clustering. And when it comes to unsupervised learning, now you're taking data that's maybe not labeled, it's not structured as well, and you're starting to identify, you're seeing trends in the data, and then you're alerting the users. And then, of course, in both of these cases, if it's real AI, you're creating some sort of an automated action coming from that, some decision tree. Hey, I see this trend, and I'm now going to do something. And that's the concept, to automate these systems. Semi-supervised, again, the mix of the two. Some of it's labeled and structured, and you've got plans for how it should look. Others unlabeled, and the system is identifying these quirks and unusual things and trends. And then when you go to reinforcement learning, that's this newer category where maybe you're doing more of a trial and error sort of approach, or you're applying several different algorithms to a set of data that may be labeled or not labeled to define if it's a cat or not a cat, as an example, or what type of language is it, or what word was that the person was trying to say. It doesn't exactly match my models, that we think this is the closest. And we're reinforcing that and trying to then grow and improve the algorithms over time as we add more and more data. So a lot of terms, and hopefully this lets you see the AI is from an advanced analytics into an automated system that's going to do some deep analysis and regressions to kick off some automatic decisions, all the way into figuring things out by trial and error is the scope of AI.
Thanks, James. So we want to talk about why everyone is talking about AI now. So what has brought it to the fore? As I said, it's been around since the 50s. So it's been clear that we've been doing work on this for a very long time. We have a lot of history in being able to build algorithms and do artificial intelligence, which if you go back into the sort of 80s and 90s, we had knowledge systems and those sorts of things. So why are we now talking about it again? And machine learning is probably the primary reason, because we're democratizing the ability to actually perform machine learning. There are open source algorithms, there are open source frameworks such as TensorFlow and Keras that have been given to developers to be able to build that sort of platform. But how did that start initially? And the reason is because we have actionable data now. We have large pools of data available to organizations, not only because technology has advanced to the point where we can store more on less and we can be more efficient and operational about how we store those pieces of data, but the law and legal frameworks are telling us we have to store this stuff. So things like data protection and protecting personal data, but also things like disaster recovery after the events of 2001. All of this says we now need to keep all of this data safe. We need to back it up and protect it. And in order to do that, if you're having it lying around anyway, there's a good chance that you should be getting some value out of it as well. If you're paying all that money to protect it, you should be getting as much value from that as you can. So we have all this data lying around, and the ability to process that data purely from computational power and bringing to bear things like accelerators and GPUs against this data as well means that we now have the ability to drill into that data. The advancement of algorithms, as I said, things like TensorFlow and Keras and the ability to create neural networks simply from well-known frameworks that are open and accessible to everybody, means that you can be a data scientist in your own front room now. You don't necessarily need to have access to large supercomputers to be able to build models and build inference engines and those sorts of things to be able to start getting into deriving value from data. The current events with the coronavirus and COVID-19 are an excellent example of this. There are many front-room data scientists that are looking at the statistics coming out of different countries and figuring out from that where areas of risk are, where money should be being invested, where there might be high populations of elderly people, those sorts of things, just from getting access to data that's there on the internet and then plugging it into models that they're building in their front rooms. Now, that's not to say that they're running quickly, but you have the ability because of the democratization of those algorithms. And of course, finally, the computing power. We can train those models now on supercomputers and on large compute systems loaded with accelerators and FPGAs and GPUs and everything else at relatively low cost. And I say relatively low compared to the supercompute of the 90s and early 2000s, when it was an expensive thing to do, when there was the data pools themselves were expensive, and more importantly, when I/O was expensive, when taking the data from where it was sat or where it was being created to where the supercomputer lived was also an expensive thing. So the convergence of these three is really driving the adoption of this technology. The other thing is you want to move up the stack in terms of gaining value from data. So if you look at how computers have traditionally been used in society, we've been very reactive with them. If you take IT operations as an example, because usually we're all familiar with these, most of the intelligence of a knowledge base is around what happened. I've seen this error. What does it mean? How did I get to this state? So there's a lot of investment from identifying a log pattern. How did I get to where I am? What happened to cause me to be here? And that's what we call descriptive. The next is diagnostic. Why did it happen? So what are the events that led to this event happening? So not just what has happened, i.e. my computer has crashed, but what made it crash? What were the events immediately leading up to the disaster or the fault, and what can I do about it? The next is what is happening, and this requires the ability to apply intelligence against a real-time stream. So monitoring logs that are actually happening. Now, if you go back to IT operations, again, we have SNMP traps and all those sorts of things going on that tell us what is happening at that moment. But even that, if you think about it, is more of a what happened, because it's an event that's triggered immediately after something that's happened. Whereas if you're looking at trend analysis of logs and telemetry coming from a compute environment, you're able to predict what's happening because you can see it happening in real time. You have the graph to interpret, to see that CPU is beginning to climb before you hit that watermark that says I'm too busy or I'm now going to stop responding. That leads us into prediction. So when you apply that type of intelligence, rather from a human looking at a graph, but into a trained model, you get to prediction, which is what will happen. Based on the trend that I'm seeing in my logs and in my telemetry today, can I tell what is going to happen next? And then finally, when you plug that into other contexts and intelligence from other business systems, you end up being able to be prescriptive. And this is saying, what should I do about what's happening? So if you think about a production line, for example, with factory machines on it, you could look at the factory machine and see that something is going wrong with it. There's vibration that's beginning to happen, or there's an increase in temperature, for example. So you know from that, you're at the predictive stage, and you're saying, well, I know what's going to happen to this machine. It's going to stop working, and I'm going to fault my production line. So adding the prescriptive layer onto that is really talking about what should I do? How should I reroute my production line through other machines, or how should I back up the downstream activity, if you like, so that I don't get a bottleneck at this machine when it breaks? Do I take it out of production now, and do I sort of pay for maintenance? All those sorts of things. That's in the realm of prescription, and that's really where machine learning is playing a huge role.
Guys, before you move on to talk about data, just throw a quick question for you, because there's a question come through, and actually I think it extends on from the previous slide, from descriptive to prescriptive. It's about volition. It looks like everybody is talking about AI, but thinking about pattern recognition and machine learning. The biggest differentiator for humans is making a decision and acting on its own without external influence. Little children are a good example. Can AI make decisions in its own right? I suspect this is a sort of volition question, and I'm sure you'll be able to answer it better than I asked the question.
So I'm going to use my usual consulting response, which is it depends. So yes, it can. So AI can absolutely make decisions because it's based on probability. So what you need to state is what threshold will you take of certain action, and that can be programmatic. So based on the probability in a deep learning or machine learning algorithm thinks it's identified a situation, what activity should it take? And you build in the thresholds at which you can take it. What it can't do is decide what activity to take necessarily, unless it's part of a knowledge base already, or it has a set of options predefined. So it's not going to figure out that based on what I see going wrong with this machine, I should change the carburetor, or I should change the oil, for example. It's not going to make those sorts of decisions unless that's programmatically available to it. So it's not going to learn new things necessarily, but it can absolutely be used to make decisions. And we'll get onto that in a little bit as well when we start looking at components of a solution altogether and how that matters.
Okay, thanks, James. Any observations to add?
Well, I think Glyn nailed it. It's definitely, you see these sorts of systems interacting together, and you'll see playbooks being built so that you can maybe help make the decision and the action happen faster. But those actions do definitely need to be programmed in some sort of a playbook mode.
Yeah, I'm thinking of things like car driving, AI for automated management of vehicles, steering, brakes, accelerator, etc.
Absolutely. In autonomous driving, you don't want to have the humans make the decision after you've hit the wall. You'd rather the car just turned or stopped before that.
Yeah. Okay. Thank you.
So the interesting thing about all of this, if you're still listening and you still care, and I'm sure if you were playing a drinking game where the word data came up in this discussion, you took a drink, you wouldn't be listening anymore, you wouldn't care. But that is the challenge that we're facing in this environment. It is a data challenge. So along with the growth of this market and all of these systems and everyone getting excited, the important part of all of this is you need data to be able to analyze and make decisions on, and you need to collect more and more data and remember that data in order to be able to then continuously learn and grow and improve. And so that creates a tremendous data challenge, and data challenges in enterprises just continue to get bigger and bigger. What you're seeing in a lot of the very early deployments of AI is that they're creating specific, unique systems, a bit like just a ball that they stick on the side of a very nice box to manage through these AI challenges and problems. And it's a common way to implement it because it's quick and easy and you don't know if you're committed, but it's not all that organized, and that creates a couple of major problems. One, we've already got data silos where systems are not necessarily connected together. We don't always have all of the data pipelining into a centralized place. We've got organizational structures that are getting in the way. We've got certain teams, we've got security and who needs to see what data. We've got different vendors, and we all want to have a multi-vendor strategy to make sure we limit our costs, but then of course they don't always necessarily, systems all work well together perfectly without a lot of work. Creates a lot of silos, so that's a challenge. The other challenge is how have you tracked and incorporated this data? Do you have duplication in the data? Do you have the right labels on the data? Are you saving data that matters, or are you just saving everything? Maybe you haven't transformed the data properly. So there's a lot of, with the ingest of data into these systems, and everyone of course has their own agendas. So one organization may look at it a certain way and throw some data away or rearrange it in a certain way that's then detrimental to another organization, right? So you don't have a good data strategy. So these challenges are huge, and when you're thinking about how you're going to design your storage, which is the core part of artificial intelligence, because you need the data and you need to be able to get to the data, you need to remember the data and keep it organized. What are you going to do about that? So there's a couple of things that we see in the industry. There's probably lots of them, but the two that really stand out are making sure that you have a centralized shared data storage architecture. So you have to be able to have some system that you can pour all this data into. And ideally, it's one system. So you don't have to have 10 systems with each of their own independent storage pouring into one larger system and have multiple copies. You'd really like to have a single copy because the costs could get astronomical as you save more and more data. So shared storage architecture is really important. Another element is to have a data lifecycle, to understand, and Glyn's going to get into more detail about this, but understand as data comes in, how long are you going to keep it? How are you going to parse it? Where are you going to push it? What are you going to do with it? And then you have to then have that plan of the pipeline. Think about it as a factory. You have to look at this as almost a chemical engineering problem. Here's my data's coming in here, and it's going to go there, and then I'm going to do this with it, and I'm going to keep copies here and there, and I'm going to move it to these systems. But you have to think about the pipeline, about which systems are going to touch that data, how are they going to use that data when it's touched, is it going to be in an organized fashion that I can manage it, that I can get it out of my system so that I don't have to have infinite growing storage, although storage vendors would love to have that happen. But so those are the opportunities that we have as we go forward. When you're thinking about this infrastructure, that's where we'll dive into next. So the first one, what's happening around a shared data storage or a data lake, as it were? You've probably heard the term data lake, and you've probably heard it in terms of HDFS storage, and it's the secondary system. Well, people are really starting to rethink that. They're starting to understand how if they can have a common repository for all of their systems of their data, that they can then more easily manage it, they can more easily govern it, they can more easily secure it, and they can make sure that the users are all serviced. But what that creates is that this opportunity to look at storage a little bit differently. And we see data lakes are taking off, and whether it happens to be some sort of software-defined storage, some sort of traditional standard NAS, or some sort of hyper-converged or converged system, they're all really growing with this concept of a large pool of shared data. And what that drives then is a need for a bit more performance that we'll get into a little bit later. So, Glyn, I think this is your plan to take it through?
Yeah, sorry, I was stuck on mute. It is definitely April Fool's Day. So when we look at data, they exist in many different ways. So it has a life cycle. So there's where you acquire the data, so where you source it from. When you sourced it, you then have to transmit it to somewhere. So that's bringing it from possibly sensors, maybe end-user devices, maybe just applications. So you're transmitting the data from where it's being generated, where it's created, and where it's birthed, and then you're ingesting it into something. So that could be a unified internal storage device. So let's call it the data lake, because the term is kind of generally used and generally accepted. After it's ingested into that, you're storing it, and then you'll be doing things to that data. And if you think about how we did this traditionally, the data generally was connected for a specific purpose. So if you think about databases previously, when you collected that data, it was generally put in a database, and that database was tied to an application, and it had one thing to do, and it did that very well, which meant you knew over time what the performance profile of that data was going to look like, how it needed to behave, how to protect it, what security and governance to wrap around it, all of those things. Today, it's different. When you start looking at building machine learning models, and you put a data scientist in front of lots of pools of data, they'll grab anything that appears relevant and they'll push it all together without necessarily thinking through, am I doing the right thing with this data, or am I bringing this together in even a moral way? But do I have the rights to do all of these things? And also, what impact does my use of this data have on the underlying subsystems that are storing this data? So if I'm on a data lake and I have a bunch of spinning disk underneath that, what extra load am I putting on that storage piece when I'm starting to do my training or my inference with the data that's on there? Impacting as well the other applications that are using that data too, because they're still using it and they're still pulling data from it. So you need to start thinking about all of those things. Also, when you're capturing data for a specific purpose, it's not necessarily in the right format or in the right means to be used for machine learning. Machine learning, you have to do things like cleaning the data, so looking for where there's gaps in the data and how do we deal with gaps in data. Do we aggregate? Do we decide on means? when we look at values within a data set, what's the range of those values? And are we going to have huge numbers that will pretty much wipe out the importance of other features, or do we need to clean them down and start normalizing them into different values? So there's all of those different pieces. And then finally, there's the integration. So now I have my data in a store that I can do different things to it. I know how to get to it, to clean it and transform it so it's ready for different things. How do I integrate it into the northbound application? So that coming on to the actions that we were talking about earlier, the decision making at some point. So those are the kind of phases of the life cycle, if you like. If we focus on that, what we call that is the data pipeline. And it sounds like it's a simplistic thing where we have a birth and it goes through the process and then it lands on somewhere as a data store and then it gets used. Where actually pipelines are incredibly complicated because they're usually multi-stage, they're possibly multi-functional in the terms of a data will go down more than one of those pipelines that you define, depending on what outcomes you're trying to drive. And there's a complexity to that. The other piece is when you're capturing data, you end up capturing a lot of data, particularly if you look at video analytics, for example. So you have a CCTV system that you might be capturing data from. Maybe it's around the public transport network, maybe it's within a financial institution, maybe it's within a market or something like that. There's a lot of data that you're capturing, and not all of it's going to be relevant or useful. So you need to do a lot of pre-processing at that stage as well to figure out actually what data here is going to be useful for retraining, for example. So how do I take this data and I make sure that what I'm keeping is going to be useful for training later and not add bias to my models and those sorts of things. So there's a certain amount of filtering you have to do. When you're bringing that data in as well, you're at the point it's being created. That's the best point to make a decision about how to act on some of that data. We talked about autonomous driving earlier. You don't want that data going back to a data center, being trained overnight, and then coming back to there with the stop answer the following morning. That usually ends in disaster unless there's an astute driver in the car as well. You want that immediately known. So you need a very fast pipeline to be able to take the data as it's coming on sensors, aggregate it and transform it in the right way, layer it on top of other data sources that it has. So if you think of autonomous driving, we have the LiDAR, we have optics, we have radar, where all these things need to come together and then go through an inference engine that comes with a probability that makes a decision and takes an action immediately. And there are very short time frames with which that needs to happen. So to be able to filter out the right data brings down the processing requirement for that real-time need. And again, that's aggregating together. The other piece of aggregating is when it does finally hit a data center somewhere, so you have captured it and you've taken it back to a data center, how can you add value to that data? Now, we talked at the beginning about what is intelligence. And intelligence is the ability to apply context to data. So you have a particular piece of information and a human being will say, I know contextually where that sits with the rest of the ecosystem that sits around it. You can do that in data by aggregating other data sources with it. So if you look at natural language processing, for example, and trying to do translations of maybe a call center, by looking at the records the call center operator is creating and other records around the customer that may be on the line at the time, you can augment those together to give the model a better chance of getting what's being said by giving it the context that it needs to make those decisions. So we end up with four primary candidates of data, really. So we have, using the kind of industry buzzwords, if you like, we have IoT sat at one end, which is the edge. And to me, the edge is wherever your business hits your suppliers or your customers. It could be in a factory if your business is creating things, and the edge, therefore, is where your workers meet the machines. It could be where your customers are transacting with you, so that could be on an application or it could be in a branch. That sort of thing. So that's the edge to us. And you're capturing a lot of data at the edge because you're having the personal interactions. That's where your customers are being the most expressive and where you can identify most about that customer's need. And I'll use customers loosely because it could be staff, it could be partners, it could be suppliers that are doing those interactions. But it's where that personality is generated and where that data is generated around how those interactions are. And let's face it, the primary goal of most business is to provide customer satisfaction and satisfy a need. So at the edge is where all of that transaction is happening, where that exchange of information is happening. The fast data is really where you're getting data from the edge and you need to act on it immediately. Back to the autonomous driving example, for example. And then big data is where you're starting to pull that fast data through. You've already acted on it, you've made a decision, and that's all good and happening on the edge. But now you're beginning to bring the data sets back into the data center so you can retrain models. You can get them smarter. You can start aggregating them with different data sets. And you need to look after data as well. There's still going to be legislation wrapped around this data, such as GDPR, so that you are keeping it in a sensible place. You are indexing it and having the metadata stored around it so you know what to delete, what's associated with people, all those sorts of things as well. And then finally, you have AI on the far end, which is where you are actually doing the training of the models, where you're doing inference against the data, and where you can use AI actually to create new models as well. So you may have all heard of AutoML, for example, which is where you use artificial intelligence to randomly, there is a process to it, but where you create new features or you create new weightings of the features within a data set in order to generate new models and new outcomes. So it's not a human being creating the models, it's artificial intelligence creating new models for itself. And it starts to get a bit scary there, and we get into the realm of explainable AI, which is beyond the scope of this presentation, but is also something worth considering. Finally, plugging into the bottom of that are those existing business systems I talked about. So the SQL databases, the SAP, the HANA pieces, the Oracle, whatever it may be, all plugging into the bottom end of that big data as well, which is the augmentation of existing data sources. Don't forget, it may not be possible to migrate them because they have dependencies on them. They have applications that attach to them today that are needed. And so you can't just rip them away and say, I'm going to throw everything into HDFS and Hadoop. It doesn't work for everything. So you have to have that augmentation of existing business systems. The long-term strategy and goal may well be to bring that data into that data pool and have it exist within the data lake still. And that's absolutely fine. But in the meantime, you need to manage things like metadata and data dictionaries so that you know where to find that data. It's discoverable by the people that need to be discovering it, and they know how to leverage the schemas to use it.
Glyn, before you just move on a second,
Sure.
We've got a couple of questions. Firstly, I'd like to apologize. If you're hearing a bit of choppy sound from Glyn, I suspect it's all the recent Netflix subscriptions and Disney Plus stuff that's going on, interfering with our bandwidth here in the UK. But the two questions were, you need to think of the security of who's seeing the data resource, and that's absolutely true. I'll answer this one. There's a whole field of AI ethics that's sprung up around training models and sets and making sure we don't end up with bias in the models. And I recommend you go and look at some of the really quite good articles that are out there about AI ethics. And on that note, the second question was, are these anonymous questions? Yes, they're anonymous to everybody else. All the questions you ask are only seen by us, the presenters, and you, the person who asks the question. So they're private in that sense. So anyway, sorry, Glyn, just to answer those two questions. I think the security one and AI ethics is an interesting one, but it's possibly not the subject of this presentation.
Yeah, absolutely. There's a huge field there we can get into, but you're absolutely right. When we start looking, and I hinted at it there when I talked about getting onto the business systems and the other data sets, a data scientist doesn't necessarily think in those terms. They think of what data they need to create the models and create the outcomes that they're trying to drive. We do need to put governance around it that says we need to consider security, so who gets to see the data and in how it gets used as well. So as I said, if data is captured for a specific purpose, there's many countries that have laws that say if it's captured for a single purpose, you only use it for that purpose and nothing else. So absolutely, but as Alex said, that's a very wide field, and I could talk for hours, but we don't have hours, unfortunately. What I do want to do is walk through the anatomy of an AI solution. So this is what components make up an actual solution. So when I'm deploying it to a customer, for example, as I've done a few times, what are the bits I need to think about? What are the moving parts? Now, the bit everyone focuses on is the model itself and being able to train the model and get the accuracy to within 99% or whatever it is that the customer needs to be. And that's where all the money gets spent. The data scientists are expensive, and the infrastructure to train models is usually expensive because it's full of accelerators. But as you can see, I've got a lot of white space still on this slide, so it's not the only part. In fact, it's a very small part of the bigger piece. I've heard it said that this is where everything starts. You start with the training of the model, and as you can see, it's sat on the right side of the diagram, not the left side. So I don't even think it's the start. It's a portion in the middle somewhere. So if we start seeing how we get the training model, it has dependencies, and we talked about the need for data already. So imagine this is a supervised model, so we have labeled training data. You need to split that into two, so you have the training data itself, and that's the bit that the algorithm will churn off against and figure out what weightings it needs to give to the various features. And then you have test data that it'll use to validate its own thinking. So as it trains, it goes through an epoch, which is what we call a one training iteration. It'll go through an epoch, and then it'll use the test data to validate its outcomes. So it'll see the photo, say, is this a cat? Yes, I think it's a cat. Let me go to the test data. I'm using my same algorithm. I think this is a cat. Oh, I was wrong. So it scores itself based on the test data it has as well. But that data has to come from somewhere. So as I said, there's a raw archive of data that sits there. That's typically on that big data lake that we talked about earlier. Could be in the business systems augmenting that as well. that has to be transformed and cleaned. So the missing data aggregated in some way, the format normalized, the large values normalized, those sorts of things. As well as getting it into a schema that the model itself is going to understand. So we're doing some kind of transformation. We're dropping irrelevant fields that might actually introduce bias, for example. So Alex talked about ethics. That could be using an inappropriate field to make a decision. So we drop them out of the model at that point as well. And all this typically happens in the data center because that's where those large data pools live and that's where those heavy machines that do most of the churning live. When I say data center, that could be public cloud. I'm not discriminating against cloud either. You could have that set on AWS or GCP or any of the hyperscalers, but it could also be in a data center. Alongside that, once you've trained the model, you have to do something with it. Otherwise, it's useless. You've trained it, you've got some great accuracy, but you're not doing anything useful from business context. You've just proven how smart you are, which is great, but not necessarily going to increase the share value, which is what most businesses are looking for. So you have to then package that model up. That usually involves a lot of optimization as well, because models tend to be big. If you've got a lot of data and a lot of features in it, so if you look at something like natural language processing, you can have millions of features in a model, which means the model can be gigabytes in size. And if you're going to deploy that to the edge to do inference, for example, or you're deploying an autonomous driving model, which has to take features from all of the sensors around it, as well as coming back from LiDAR and images, that's a huge model, but you need it to act quickly, so therefore you have to go through optimization. That's taking out layers that would otherwise be redundant or cause delays in inference, or just cause heaviness to the model. Then you need to distribute the model. Now, when you're distributing the model, it's worth thinking about how you secure the model itself as well. I've done some work with financial services, not in my country, in other countries, whereby they let me play, and they said, here's our model distribution framework, have at it, give us a point of view of how good this is, or haven't we done well, essentially was the prompt I was given. And what it turned out was I could inject my own model into it, so I made a fortune. It was in their test environment, so it wasn't a real fortune, which is unfortunate, but it meant I could change the model for one that favored me, and I was able to trade ahead of them and figure out how that I could influence their markets in my favor. That's what happens when you don't understand the model security aspects. So how do I sign the model so that I know what I'm deploying in my inference engine, in financial services or in medical, this is critical. How do I know the model that I trained is the one that I've deployed? So you can do fingerprinting and SHAs and all those sorts of things. There's also the management of the config of the pipeline itself. So I told you have to do the transformation and cleaning. Well, you're still gathering live data. So live data is going into the inference model more often than not. So I need to make sure that whatever is happening from a data transformation aspect and a data cleansing aspect, that my data scientist has defined at the raw archive to training data phase, I'm also doing in live the same way. And those two things need to stay in sync. So when I deploy a model that's been trained with a specific format of data, I know that format of data is coming into my inference model for pushing out the other end. And then finally, back to the decision piece. If you don't commit an action, and an action could be I'm rendering it on a graph so that a human being can look at it and take an action, or it could be I'm actually programmatically taking an action, so I'm turning the car left or right or stopping it, or I'm executing a financial trade, for example. Unless you have that activity piece, and that gets forgotten in a lot of conversations, it's basically the equivalent of hiring the smartest person you can find and locking them in a room and not having them do anything. They're coming up with great decisions, but nobody's taking any notice of them and they're ignoring it. So when the question came earlier about can it make decisions, it absolutely has to in order to get the value of being able to make these probability guesses at the speed at which AI can do it. Obviously, there's elements where you won't have speed, and the decision will come at the end of maybe a day's worth of churning away at it. That's more going back to the simulation that we would see in high-performance computing rather than what we expect from an inference model. Inference, we tend to expect an answer to come out within seconds, if not microseconds.
So one of the things that tends to get overlooked or not talked about enough, in my opinion, is how the hardware meets the software, these pipelines and all of the processes that we talked about. When we talked earlier, we said there's a centralized data storage is a really good way to help manage some of this, or maybe groups of centralized storage systems, as well as then the data pipelines. So Glyn took you through the data pipelines. When we talk about the hardware and how it meets, there's a few important factors that people really need to think about. You've just heard all of these different systems that are going to ingest the data and transform and clean the data and train models on the data and then do some inference and package up those models and distribute them and all of these elements. But what does that really mean from the storage systems and hardware? The first thing we need to think about, if we are going to deploy it in a data lake, we have to remember there are going to continue to be all of these traditional systems that are continuing to use this data in some fashion. and they need some level of performance and access to that data. So that's your traditional storage performance that you've always had. But now you're adding in all of this additional new data and all of these new processes onto those same systems, and they're going to have some interesting performance impacts. So there's a nice white paper that we've got in the backup that you can go through a lot of this detail, but I'll just talk briefly about some of it. You may have some sort of a caching or streaming layer, some sort of an ingest layer, and you can think about that ingest layer is it has, an example might be something like Kafka, producers and consumers. There's large amounts of data flowing into the system, and it's usually flowing from many sources, and then it's usually being transmitted out to several consuming systems, and it may be one or it may be several. You may be storing it for a short period of time or a long period of time. But what that does is creates as some sort of a significant write-read ratio, writes from all the data sources, as well as then reads, and not at a predetermined time necessarily from separate systems. It's all asynchronous, and that's going to put a large performance tax on your storage system. Usually tend to be small files and very random. You can then look at, say, a data prep phase where you might be doing extract, transform, and load. You might be doing some sort of data processing. You're reading it in and writing it out, again, sort of a 50-50 mix. So you've got a lot of these 70-30 and 50-50 mixes, 70-30 writes reads, 50-50 reads. It's all taxing the data lake. And then, of course, you're going to be doing training. And those training will be asynchronous. You'll have your team of data scientists pulling out and doing some sort of a training on a small set of data or a large set of data. They may be batched and planned, but they may be asynchronous, and all of a sudden you have a very large read, and it's probably a lot of random read, where latency is really important in order to make sure that those maybe not necessarily wonderfully written algorithms, maybe they were written without a lot of error containment. So if you have latency hiccups, the systems could crash. All that means you really need to think about the storage performance of your data lake, and we see a few trends in that environment. We see shared data lakes using newer technologies. Software-defined storage continues to get faster and faster. People are looking at different ways to address the data, be it object or be it traditional file. But you have to look at those, and we're also seeing, even in the core data center, hyper-converged infrastructures being utilized because the central access and ease of management of that data really changes the game and allows you to deploy that AI. And the other thing we're seeing is at the edge, we're seeing there's a centralization of a large data store where you're doing most of your training in the center somewhere, but you're also reducing the data at the edge and inferring at the edge because you don't want to consume all of your bandwidth sending all of the data that you may have decided you don't need. And so as you learn from this, you may be stripping it and doing some data prep at the edge. And then you also have some systems at the edge that aren't just doing training and inference. You have some standard business processes. Maybe it's a grocery store and you're running your inventory, or you have some sort of a photo processing, or maybe a pharmacy. So you have a large amount of data at the edge that's happening at the same time as you maybe are doing some AI, recommending to the person at the retail outlet, hey, you might want to recommend this product for them while they're checking out. They might be interested based on their buying habits, or give them a coupon to get their loyalty. In all of that, the key here is this data problem, large systems. You don't want to have multiple copies of the data if you can avoid it. You want to try to minimize the bandwidth between these systems, and you want to make sure that the storage system has enough performance. So you need to think about building a system that has more performance than what you're anticipating right now. And that mainly is because of that market growth I showed early in the presentation. You're going to be adding more and more AI. It is going to be critical for your business. You need to over-provision storage performance right now, else you're going to be in a world of challenge, having to retrofit and redo something several times. So that's really the key to managing the pipeline as well as the data challenge. So when you look at that as we go forward, you have to think about, you'll have a very large need for capacity, and of course performance becomes expensive. You'll have some need for performance, whereas you'll have to decide on the system you're going to utilize to support all of these workloads, the legacy workloads, your new workloads, and of course all of the new storage performance that this dynamic artificial intelligence system is going to add to the system. Also, you have to think about the capabilities when you look at this system. You have to understand how you're going to manage it. Are you going to have some global namespace? And of course, security we talked briefly about, with some security controls. You're going to have to decide what you're going to keep where within that system, because it may be a tiered system in order to manage the costs. So what are you going to have in the high tier versus the slower tier? What are you going to do in terms of managing your data and your data governance? And then how scalable is it? Can I grow it? And is it going to grow over time, and is it going to meet the needs in case I did over provision but not quite enough, because I don't want to spend infinite dollars? So it really presents a lot of challenges, and hopefully we've given you some of the ideas to think about. With that, I'll let Glyn close it up.
Thanks. So to summarize it, AI is definitely more than just training models. In fact, the training models turns out to be probably the easiest function of it. Managing the data, managing the flow of the data through the business and through the infrastructure is the toughest bit, and making sure that it's stored in such a way that it can be multi-purpose. Data doesn't have a single purpose anymore, no matter how much we would like it to. It's purpose plus now, which means whatever you think you're capturing it for, it's actually going to be used for other things, and you will have no idea what those other things are at time of capture, because a data scientist will come along much later down the line and have new ideas about how to use that data, how to leverage it, and how to get value from it. So we need to think, how do we give flexibility to data purpose, not build it for a silo? We need to simplify and unify the way we treat data. We have to have a single pattern that we can apply to data capture, to data storage, and to data indexing and metadata management that allows it to be unified across the entire infrastructure, from the edge where it's being captured and where we see the fast data, through to that unified data platform in the center, through to the consumers of that data. That means we're moving towards shared data storage architectures. We can't think in terms of silos anymore, because that locks data away, and we're discovering the value of data is in the ability to apply that data where it's needed, not where it was captured and not for the purpose it was originally intended for. That unifies the entire data lifecycle end to end. Pipelines are really the new SAN. So where we used to see data being generated at the computer, go down the SAN and hit a lung somewhere, we're now talking about data pipelines, which are far more complicated, have processing involved in them, do things to the data as well as store it and end up somewhere. So those are the things we want to talk about, and I'll hand back to Alex to close.
Thank you, Glyn, and thank you, James. And just to add to this, we've got some links you might want to follow here that take you a little deeper into some of these subjects. One of them is really interesting. This may appear to be a very new topic for a lot of us, but in fact the SPEC committee, which do benchmarks, already have a benchmark that covers AI, ML, and genomic workloads. So if you're interested in actually benchmarking any AI or ML solutions you're putting together, they can help you do that. And there will be further information in that particular presentation that you see in the second bullet item. I'd like to thank everybody for coming today. I really would. It's been a pleasure, as usual, in doing these presentations. I'd like you to do me one last favor. As you leave the presentation today, if you could actually rate it and provide us with feedback. We do look at all the feedback. We do take great pains to make sure that we take on board any criticisms and suggestions you might have. And if you would rate that presentation for us to give us an indication of whether these kind of presentations are what you're looking for, what kind of further presentations you would like to see, what we didn't cover that we should have covered, etc., that would be incredibly helpful. The PDF's available currently. You can download it from the attachment, and it will also be available on demand along with the presentation. The presentation will be available on demand along with the slides at that link address there under the SNIA website. We'll also be posting on sneacloud.com a Q&A from this webcast. We've got a few questions, and we're going to take those and add to this presentation and hopefully round off those questions for you. You can also follow us on Twitter. We're actually on Twitter, at sneacloud. My many thanks to you today. I hope you've enjoyed this presentation, and wherever you are, take care. Thank you very much indeed.